Hi, everyone. I've got a previous diploma question here that tests Voltaic cells. And the question here says to design an experiment that would allow us to test the student's hypothesis shown above. But what I'm going to focus on in this video is just simply labeling the lead iron Voltaic cell, and we'll write the balanced equations that go along with it. So first of all, I need the containers that I'm going to use to build or draw the diagram for the lead iron Voltaic cell. So let's start here with beakers for each of the half cells and the electrodes that are going to go into these half cells. They're connected by a voltmeter and a salt bridge that would just contain an ionic salt solution. So now it does not matter which side is labeled the lead. I'll just choose the left side here, and which side is labeled the iron. So I'll just label those, and then I'll put the corresponding solutions that they're in to complete the redox couples. So the lead would be in a lead solution, and it would have been brought in with an anion, something like nitrate. And the iron would have also been brought in with a nitrate ion or something that's not going to react. So I'll just write it as nitrate. And this is the salt bridge that would include something like potassium nitrate. So I'll just go K plus and nitrate. So there's the components of the cell. And now what I want to do is decide which one of these is the anode and which is the cathode. Now we can see here that the lead is at negative 0.13 volts electrode potential on our reduction half reaction table on page 7 in our data booklet. And the iron is down at negative 0.45 volts. So the iron is actually lower on the right-hand side than the lead solid. That makes this iron the SRA. And it's going to react with the lead's solution. So the lead 2 plus is actually the SOA. That's the reaction that's going to occur. Now the SOA is the oxidizing agent that reduces, and that occurs on the cathodic side. So that means that this side is gain of electrons is reduction at the cathode. That makes the lead the cathode and the lead ions the catholite. So the iron is the anode and the iron solution is the anolyte. Okay, so if the anode is the iron, this charge of the iron anode, or the electrode at the anodic side, is negative, and the lead is positive. Okay, so the cathode for a voltaic cell is always positive, and the anode for a voltaic cell is always negative. Now we know that the electrons are going to go from the anode to the cathode, because the loss of electrons, I'll write that down as well, the loss of electrons is oxidation at the anode. So there the anode is oxidizing, losing electrons through the external circuit, and picked up by the cathode, which is the gain of electrons. And the reacting substance is actually the lead ions in the solution. So there's the solution containing those ions. So the only other thing that we need to label on this diagram would be the direction of the ion flow. So I'm just going to show it this way. Actually, I'm going to use just a different color ink here. Okay, so let's put the ions flowing this way. So through the salt bridge and from the salt bridge, the cations, just squeeze it in here, the cations are going to flow toward the cathode, and the anions are going to flow toward the anode. So they flow to their respective electrodes. Okay, now I'm going to just move down here and I'm going to write the half reactions. So the first one I'm going to write here is the lead 2 plus ion, which is going to gain 2 electrons to form lead solid. That's the gain of electrons that's happening at the cathode. And then the iron, I'm writing this reaction in reverse, is losing electrons to form the aqueous lead, iron ions. I'm also going to write down the reduction potential at the cathode. So the standardized value that we see for the lead, as I mentioned before, is the 0.13 volts. And the standardized value for reduction at the anode is the negative 0.45 volts. So here I can write down my net reaction. We can see that 2 electrons are gained, 2 electrons are lost. So the end result is the lead ions plus the iron solid, that's what's actually reacting, is producing the lead solid and the iron 2 plus ions. So if we check the reaction is balanced and there's 2 plus on the left-hand side, 2 plus charge on the left-hand side, and a 2 plus charge on the right-hand side. Let me just use a different color here. So there's the 2 plus charge and the 2 plus charge, showing that the redox reaction is balanced. Now, if I actually subtract these electrode potentials, I will get negative 0.13 volts minus the negative 0.45 volts. So it's actually like adding the 0.45 volts. And when I do that difference, I get a cell potential of positive 0.32 volts. Now, the fact that it's positive means that it's a spontaneous reaction, which all voltaic cells are, and it's a very small potential, but that's our cell potential. And then lastly, what we see here is we get lead solid forming. So this solid forms, and we know that this is the cathodic half reaction. So this is at the cathode because it's the reduction half reaction. And there's no significant color of the iron solution. But if we look at page 10 of our data booklet, we can see here that the iron 2 plus is colorless at low concentrations, but it could start to form a lime green color at higher concentrations. And that could be evidence that the reaction is actually happening. Okay, the other thing is that we could potentially see corrosion. Let me write that again. Corrosion at the anode of that iron metal. Okay, but in this cell, it's going to be so insignificant that we don't necessarily visualize that or see it. So this is the basics of a voltaic cell, where we label all of these components like electron flow and ion flow, the charges, the anode, the cathode, the anolyte, the catholyte, and decide which reactions are occurring, which half reactions. So the lead is gaining electrons, which reflects the gain of electrons at the cathode, and the iron is losing electrons, which is the loss of electrons, oxidation at the anode. And then we calculate our cell potential. So there we have a general voltaic cell. See you next time.